Hi guys, welcome to my YouTube channel. So in this class we are going to start with the as we discussed. So today we are going to discuss more on the current movement by individual electrons and holes. So first let's take an intrinsic semiconductor. So in this intrinsic semiconductor there is no doping and nothing is happening. So here what will happen at t is equal to 0, we know that even the semiconductor will act as an insulator. So there will be no movement of electrons and holes. So that will be act as an insulator. So this we discussed many times. So if we take the example of T is equal to 300 Kelvin, then what will happen due to this applied voltage, there will be an inbuilt electric field produced. Based on that, there will be some movement of electricity, electrons and holes. And also because of this temperature, some kind of electrons will jump from its bond and it will also contribute some electron movement. So like this way, there will be a movement of electrons and holes and that will be contributing a current or net change in current movement. So there will be two type of current movement that will happen in case of an intrinsic semiconductor. So we may not know that there is what is the majority charge carrier. So on intrinsic we will consider both to be a same. So IN and IP. These are the electrons current and holes current. So this is nothing but the electrons current, means the movement of electrons which is contributing the current. So that we will be defining as electron current, and movement of holes which is responsible for the current. So that we will be stating as the holes current. So let's see a detailed differentiation between both things. Like let's take IN and IP. So first point what we can say is that an electron is moving in conduction band. So electron will always move in conduction band. So electron is moving in conduction band. And opposite to that, what we can take, the hole is moving in valence band. Or an example, what we can say is the similar. Let's take all thing as an electron. So an electron is moving in a valence band. So this will be the same thing. The electron or holes the same equivalent because it's an intrinsic, right? So electron is moving in a valence band. So electron is moving in valence band. Even we can put as a hole, there will be nothing, no difference between both things because it's an intrinsic semiconductor. So electron movement in valence band. Electron is moving in a interatomic gap. So electron, because of the temperature, there is an electron movement. So electron is moving in interatomic gap. Because of the crystalline lattice structure, there will be always an less tightly packed. So that will be contributing some movement of flux, movement of electron for current. An electron is moving from one covalent band to another covalent band. So there is a slight difference because this electron will be defaultly present because that is for core kind of outermost shell, that is movement of electron. But in case of the hole to be produced, once the electron jump from its covalent band, then only there is a creation of hole. For that representation, we are making here is the an electron is moving from covalent band. So number of electrons moving out of covalent band will be contributing to the number of holes. So holes is not actually it's presenting. Holes is what resembles is that the absence of electron. So that is the equal. For an example, plus and minus have opposite, right? So phi is there. If we remove phi, there will be nothing. Minus phi we state, right? Similar to that, the absence of some values is replaced by the negative. But here the absence of electron will be replaced with holes. So electron is moving from one covalent band to another one. So from covalent bond to second covalent bond. Third point we can state is the free electron is moving because ultimately free electron is going to contribute. Free electron is moving. Here the bounded electron which is get picked up or get exited, that will be contributing. A bound electron is moving. And fourth one is that electron is moving at higher energy level. electron is moving in higher energy level, like it's a condension band, higher energy levels, higher surface energy levels. So here fourth part is the electron is moving at low energy level because this is a force. Electron is moving in lower E levels, energy levels. Okay, I hope this is making you sense. So let's take another one quick representation of both the contribution of currents. Like there will be a net applied potential because of the voltage, the electric field will act in this direction. Like the electric field will act in this direction. So this is some. Based upon this thing, there will be movement of electron in conduction band in this direction. Because of the electron movement in opposite direction, every time the electrons will move in opposite direction of the electric field. Let me draw the arrow marks in order to make it easy. So electric field is acting in this direction. Then what will happen? The electrons will move in this direction. So once there is a movement of electron in opposite direction, then the current contribution will be in the opposite direction. So there is a current which is contributed by the movement of this electron is IN because this is an I. This is contributed by drift because this is happening because of this applied voltage contributing inbuilt electrical field. So this will be the movement of electrons because of drift. Next, what will happen? There will be movement of poles. That is will align with the direction of electric field. So the net movement of holes will be aligned with the direction of electrical field. For that, there will be some production of current. So that will be aligned in the same direction. So pole movement is in this direction. This is poles. So the IP, which will also be in this direction. So the I net, which will be equal to IP plus IN. So we can simplify this into NQ mu N EA plus PQ mu P EA. So this is a formula. Like what we have done is that we have converted the I into JA. Like JA, we know that. From that we are making use of this formula. Like conductivity formula we are imposing here. So this is what the net thing. In intrinsic, one important parameter is that both N type and P type contribution will be equal. So N which is equal to P. These two values. We know that the free electron concentration and the free holes concentration will be same. So this is what the total thing that we got. So in order to increase the current, like if we have to increase the net, I net need to be increased. What are the things that we can do in intrinsic semiconductor is that without changing, if there is no change in the electric field and area constant, then what we can do? Simply we can increase the temperature. So if we increase the temperature, what will happen? N and P will increase. So that the net change in I net will increase. So this will cause this to happen. Okay. So this is one idea. But this is not recommended because after 300 Kelvin, what will happen? The conductivity will also be decreasing. So instead of increasing the temperature keep on, we will be coming into another one important idea of doping. So without increasing the temperature, we can able to attain the increasing amount of electricity. That how will happen? We will see that is in extrinsic semiconductors. So in next class we will be seeing that. So I hope the intrinsic semiconductor understood for you. So nothing. Intrinsic semiconductor is pure substance. When we apply the voltage, there will be a production of inbuilt electric field. Based on the inbuilt electric field, there will be some movement of electron and hole that is contributing current. That is what the simple thing that we go for gone through. I think this is clear to you. If you guys have any doubt, please bring in the comment section. For sure, I will clear it. So stay tuned for the next lecture. From next, we are going to see about the intrinsic semiconductor, which will be more crazier. Like what we say, it will be very interesting topic for us to understand. So stay tuned for the next lectures. Thank you.